Thanks very much, Dan, and thanks for the kind introduction. I think the first thing that I want to point out is that all of the stuff that I'm presenting today is made possible not just by me, but by a team of lots of other hardworking people, including several people in the audience. And I think that really the body of knowledge that I'm going to be talking about, especially with respect to our own platform and the vagaries of that, is due to the hard work of those students and postdocs and other faculty members. And I'm very proud to have been able to work with them. As Dan mentioned, the goal of these two pieces of tutorial is to first understand what are the control challenges of any kind of cyber physical system, and go beyond that to think about, once we've figured out what we might want to control about them, what do we do with the data side? What are the data that we're going to be using, or the ways that we can acquire data from these systems in order to do meaningful control with them? And I considered a few different ways to bring this up and to talk about really kind of the state of the art and state of the practice today, and realized it would probably be a week's worth of talks about the many different ways that individual companies right now who are building self-driving cars, or universities who have automated cars, are building those vehicles. And there's no way to present on an even footing, hey, this is what so-and-so is doing, and there's been advancements at Waymo, there's been advancements at Uber, there's been advancements in CMU's car, there's been advancements at Clemson. So there's lots of different vehicles that are at lots of different institutions. But I want to boil it down to kind of the fundamentals and why those fundamentals matter. And the first fundamental to think about for any of the vehicles that you might consider automating to do something with is that they do have to have some sensor capabilities. This is in part perception of what's going on in the world around them, so that they'll understand obstacles that they may need to avoid, or lanes they may need to keep in, other vehicles that may be around them, or where they happen to be, so that they know whether the next intersection is something that they may turn on. And we'll talk, especially in the data section, about much more about the kinds of information that you can get from sensing. But really, what I'm highlighting here is that you might have a camera on board. You may have a LiDAR system, such as this LiDAR, which is spinning around and giving you a 360-degree picture of the world. You certainly have sensor information coming from within the vehicle, as in terms of what's the state of the vehicle, the angle of the accelerator, its current estimate of its velocity, what angle the tires are at, et cetera. And you may have some front-looking information that's coming either from LiDAR or from radar about the environment around you. And again, we're now in this vague area of, does this vehicle matter, or can it be different for all other kinds of vehicles? There's lots of configuration management for the sensing that you might have on any car. And that sensor configuration management is something that's largely left up to the end developer. But you do have components that you're going to need to integrate in some way. In terms of a second kind of fundamental, we are talking about control in this talk, and there are lots of different things to consider when it comes to control. First is that you do have to ingest some of the sensor information. But the second is that control happens at many different layers. You might be controlling from the sense of giving high-level direction to a car for where it should go. You might be injecting a trajectory that you'd like to follow. You might be giving advice on what the speed limit is. Or you might actually be sending voltage to a regulator somewhere on a vehicle. And so we handle that through layers of abstraction, and we'll talk about some of those layers throughout this talk. And the third big piece is the communication piece. So we have layers to manage our control. We have layers to manage the sensing and how the sensing data are captured and in some cases forwarded on to other pieces of information. This communication piece is necessary because of the way that cars are built now. And also necessary for anyone who wants to do serious research on a car, as apart from serious building of a car that you want to sell. Because if you want to do research on a car, you're probably going to want to show up with your laptop and plug it in, and then have your laptop try something that you were trying before and see whether it works. If you want to have everything all on one computer that doesn't have any communication at all except for wires plugged into it, then you're looking at hours or maybe days of delay to take a simulation that you ran, port it over to the operating system for the car, make sure that you don't violate any runtime or real-time guarantees, and then to test it on the car, and then realize, oh, I had a negative sign error, so I need to go back and do it all again. So by communication, we're able to mitigate a lot of the challenges that come about with respect to the delay or the ability to rapidly test something and to validate that something's working by isolating it as a component. With the sensing and the control and the communication aspect, we can see that there's a lot of different pieces of any car that might be of interest or of use, but I want to distill these things down into kind of three common pieces. These are that we're going to involve a significant amount of computation in order to carry off what we want to do. We're going to have a lot of configuration management to manage and control, and especially in the testing phase, we might be checking lots of different configurations for safety analysis. And finally, we want to build a lot of models for how we're going to do the control, how we're going to ingest data and make sense of it, how we're going to be showing validity or safety or unsafety of any particular component that we want to try. And I think the biggest pieces of interest to those of us who are here for the long program at IPAM are the computation side and the model side. And this is where there's real innovation at a fundamental and abstract level that we'd like to consider. Because I, for one, am interested in building models out of data, and those models can have some use because we'd be able to analyze them or say something about them in a way that breaks through some of the challenges we have in abstraction now. And from those models, we can, in many cases, directly write the computation that we can do in order to affect those models. But the final thing that I want to mention again about configuration management is that thinking about the many different kind of configurations that you might have is what makes those models interesting or challenging. Because if you want to design something for just one car, it's much easier than making it work for lots of different cars. So robustness to different kinds of configuration management may require its own new theory in order to make sure that things are working there. So where does this break down in terms of what we'll talk about in these 2 days? Really, part one is focusing on some of the challenges that are here for control of any kind of cyber-physical system, but especially autonomous car. And the sensing plus communication leads to data. And these data are largely what we're going to be talking about in part two. And what I'm hoping is that after we get through part one and part two, what you'll have is a sense of, if I want to do something, this is how I go about doing it. And this should really, I hope, feed into some interesting discussions in our office hours, as well as some tutorial sessions in between tutorials and workshops where we can get some meaningful things done as a group. So as I mentioned before, it's kind of impossible to cover all vehicles that are out there. And I'm going to be using primarily the research test bed that we've developed at the University of Arizona as an exemplar for what you might see. I want to re-echo here that the test bed that we've built isn't indicative of anybody else's architecture, anybody else's test beds, except for the fact that we still get data from the environment and we still send messages to control our vehicle. And so once you've kind of got those two pieces down, you'll see why some of the architectures that we have can be modified to work with other kinds of vehicles. As we go throughout the fall program, and as I talk a little bit about it today, the test bed that we've developed here is an open source test bed, meaning that you can download almost any program that we've run on it and run it on your own machine if you're willing to install some things on Linux and then perhaps install your own Linux virtual machine. This is something that I think that we're going to have some set aside groups for people who want to try some of the tests of stuff that we're going to do. And I think we had in the original plan before the catastrophic events of the last 6 to 7 months, we had a plan to actually have the vehicle there in between pieces of the program so that people could do meaningful experiments or analyze data of specific things that they wanted to see or try out new kinds of controllers that they devised. And we're going to work out some way for those who are interested to still do that. It would just be that me and my team will be the people kind of Skyping with you while we do it in order to make it work. But the important aspect of this is that you can test and validate stuff on your own machine and then show us the results of that and have that outcome be something that we can then just download your code and run it on the car. And this has been a successful model that our team has used for about the last 7 years or so with summer undergraduate researchers, where in less than 10 weeks, they've come up with something useful that they would like to do with the car, even at like a sophomore and junior kind of level. And so it's a much smaller time scale if you're already familiar with things like MATLAB and control. And so I'm setting this here so that if you want to try to download some of the stuff in between now and Monday, it would allow us on Monday to have folks maybe follow along with some of the data-driven stuff that I'm going to be doing then. The test bed and many other research test beds that are out there for robotics operate on ROS. And so without going into too much detail on it now, because we'll talk more about it later, it allows us to build high-level models of the system and then generate code from that system in order for the system to behave like it does in simulation. And it allows us to test first in simulation before we go to put it on the real vehicle. And so the real advantage to doing this is that you don't have to be a coder expert in C or C++, which is the only language that we permit to run control commands on the car. But once you're able to develop something that is successful in MATLAB, that you can take that MATLAB model and do something like this to have the car drive around. We do have some safety things built into the car to try to prevent collision. And so in this case, you can see that an onboard system detected that there may be somebody living inside this structure, and probably we should stop driving before we collide with it. And if I really wanted to, I could wait a little bit longer in this video, and you would see that you would clearly resolve the situation just by picking up your car and moving it, except that you would then find the same obstacles. So what would you do if you were playing with this in your sandbox and you were a child? Clearly, you would just pick up the house and move it. And then once you've picked up the house, then the car is going to be able to continue driving as long as there's nothing else in its way. So the goal of this is to talk about some of the challenges in actuation really involves safety and keeping in mind the safety of your system as you were to drive it along and do stuff with it. If you just kind of go out and fiddle with it like you would a robot, you could do some really bad damage to yourself or to others. And so part of what I'll be talking about today is the culture of safety that you have to have when you're testing with autonomous vehicles. That feeds into desires to have other pieces of your system providing some kinds of proof that they seem to be working. And then I think I'll probably just skip this, but it's enough to say that we got a bunch of computers in the car and they record stuff. So we'll just move on from there. The different layers that we have that are built in, and again, these are things you'll hear about more as we go through a tutorial on how you would control any kind of car, really reflect the kinds of data architectures that exist in vehicles today. If you were to go into your vehicle and start looking under the dash, you would see wires everywhere. Even under your engine, you see wires everywhere coming out of the engine. I don't know any of you who might be gearheads like me. I used to have this car that was a 1970s Mercedes diesel vehicle. So there was one wire in the engine compartment, and that came from the battery to the starter. Everything after that, there was no wires. There was no onboard vehicle management. There was no knowledge of the current state of the pistons. There was no memory that the valves were knocking because there was something wrong with the richness of the injection. There was no information about whether the water pump was on. There was no knowledge of really how fast each individual tire was going, because there was probably only a sensor on one vehicle that ran a little spinner that came up that connected to the back of the dashboard that made the odometer turn and then made the speedometer turn as well. But cars today are very different. There's wires everywhere. Probably there's more than 100 electronic control units in a vehicle that you've driven, unless you're like me and you really love old cars. So what we're able to take advantage of in situations like that is that there is a significant amount of data on board vehicles today that we can take advantage of in order to find out the state of the car. But you can also use those same wires to inject control into the car. You just have to know what layer you need to be at in order to inject that control. So typically that's a kind of a low level, and injecting control can either be sending a direct message on the CAN bus to the vehicle to turn the steering wheel, or it might be that you have a connector to the electronic steering controller where instead of detecting that the driver has turned the steering wheel a little bit and the electronic power steering should add torque to the vehicle, you just send a voltage to the steering wheel and it pretends like the driver has turned it, and therefore it adds torque to the steering wheel. So there's a lot of different ways to affect this kind of control. And again, every vehicle might be different. And so what I'm going to focus on is the fact that you really need an interface to think about. I would like to have the tire be at this angle. I would like to have the tire turn at this rate. I would like to have the accelerator at this angle, or I would like to have the car be driving at a certain velocity. And then I think maybe only one or two more things before we start looking at some specific details instead of generalities. As we go through some of the remaining lecture today, you'll see that we do have some ways to visualize in 3 dimensions kind of what the car is doing. And this is through a tool called Gazebo. There's some active research right now, which is determining whether we should allow Gazebo to actually simulate the kinematics and dynamics of our car, or whether we should simulate those in a separate process and just provide updated position information, which is some of the ongoing work of Rahul Badani, who's one of the long program participants as well. So it seems great, right? It seems like this is super easy to do. All you have to do is inject a command and everything will be fine. This gets to why control of cyber physical systems is hard. So even though we have data that are coming in, there's delays in those data. So the sensing that you're doing does take time to communicate. There's a fixed rate of communication for almost everything on a car. Instead of being data-driven that something happened and I'm going to send an event, it's event-driven, which means, or so event-driven that something happens and I'm going to send an event that this thing happened. It's almost always time-triggered, which is that I'm going to be sending information at 20 hertz or at 5 hertz or at 0.2 hertz about what's the state of the environment or the state of the vehicle. And so you've got a worst case and best case estimate of when you might expect to see anything from any part of the system. And in addition to those sensing delays that are part of the networking, you might also need to filter the data, which is going to cause additional delay in understanding whether something interesting actually happened. Likewise, because we're talking about a physical system, you're going to see delays in actuation and delays in dynamics that are based on just the fundamental physics. So you have to take those into account. And this is what I have, sort of two examples on this to remind us of how hard that is when it comes to steering, because steering is one of the most difficult pieces there. So where do we correct these limitations? It comes from the software and algorithms that we're using, which are at the highest level. And that, again, is kind of at the MATLAB level, if you want to think of it, where the implementation might be. We still need to know low-level information from data about the vehicle so that we can know how it seems to be behaving and what its physical properties are. But we also want to know how we can correct for those, and that's where we rely on a lot of knowledge from control theory and control systems. So I want to start with a surrogate. Instead of talking about a car now, I want to talk about what's known as the Turtlebot. So I'm going to just pull up a quick example here, which may work. We were testing earlier to see how these things went. So can everybody see my screen still with Ubuntu still making things happen? If you're really good at cybersecurity, you could probably have figured out my password just listening to my keys click there, which is why I switched to a phone so that it would be harder to hear the high frequency noise. Okay. So I'm going to type a few things here. One of them is that I'm going to start up something called ROS Core. I'm killing it now so that I'm running the right one. The second is that I'm going to ROS run turtle sim node. And this is going to give me something that is not a car. I don't know if you can see, it's kind of small, but I have a little turtle here. And the next thing I'm going to do is I'm going to make that turtle move around. ROS run turtle sim, keep misspelling turtle teleoperation key. So as I do this, if I, on my keyboard, press the right arrow button, I can see that the turtle moves. If I press the left arrow button, that the turtle moves left. If I push forward, the turtle moves here. And I can actually interrupt as time goes on to make it show something. That's almost a J, right? Okay, so I've spelled the first initial of my name with a turtle. It's kind of hard. I was having to push buttons and make things happen. What I want to show next, though, is what's happening behind the scene here with a specific kind of message that you can identify. So I'm going to look first at all of the topics that are published in ROS and see that I have a turtle here. That turtle has something called a commanded velocity. So let's just list or just echo whatever is coming through for turtle 1 as the commanded velocity. Well, there's nothing happening right now. But if I come back over here and I turn the arrow key, so I press the left arrow button again, this actually sent a message. It was a message that said, do not move in the linear with linear velocity in any way, but please change an angular velocity at 2 radians per second. So if I were to go back and press that again, but press forward now, so I'm going to press the up button, you can see that back over here on this page that at this point it tells me please go straight at 2 units per second. And then it goes for 1 second and just stops. So at that point, we're not actually seeing any information in the rotational angle. We're just seeing the ability to travel directly forward. So why was that interesting at all? Well, it was interesting at all because if we look at some of those outcomes from, and I'm going to skip the next slide because it was the backup in case Unix didn't work. How does the hurdles help us with the car? It helps us because if we go and look exactly at what the cat vehicle is doing, we've designed it in such a way that we're using the same kinds of messages. And so if you can make something essentially work for a turtle, it might work on a vehicle if you don't want to install all the crazy infrastructure. So going back now to Unix to look again, or to Linux, I should say, Ubuntu. Now I'm going to close a couple of these things. Oops. Yeah, okay. So here I'm going to launch our vehicle, and I've created an environment that the vehicle can operate in, which looks a little bit like a neighborhood. It's very similar to the video example that we saw before. And as this flies up, you actually don't see anything, and it's because we have the ability to run it without visualizing what's happening. So as expected, something here actually seems to be broken. We'll see whether, whenever you see red text, it usually means that something not great is happening. But I'm going to look now at the client that shows us what's actually happening in the 3D environment, and hopefully we'll be able to see that our car pops up. Some of these red things are red things that pop up every time, and some of them are actually not a big deal. Earlier, I converted to the phone audio because at this point, the fans on my computer sound a little bit like a rotorcraft that's about to take off. So this can be quite intensive to make things actually show up. And because I'm sharing my screen and doing a lot of other things, it can be very computationally intensive. So I'll give it a second here in case it decides that it's going to be able to show something. Or I may just skip it and move on if it seems like it's going to be misbehaving. All right, I'm calling it that it seems to be misbehaving, so we're going to skip out of the way here. But I did create an example that would show what would have happened if we'd been able to do this. And so if you're able to open up some of these items and your computer is not overwhelmed with whatever else it's doing, we can send commands to our car, which are the exact same kinds of commands that you saw for the Turtlebot, which is that we have some linear speed that we're adding. We have some angular information that we're adding to. And if you're able to do that, you're able to see that the car will move around as long as you send those commands often enough. So as I talked about before, there can be challenges with safety. And in those safety challenges, I'm going to mute my video here for a second as my coworker comes through. You know, as we see many of these things happen with a person who's trying to control a vehicle, if you send a command and disconnect your network, you want to make sure that the vehicle stops at that point because you do not want the vehicle to crash based on the last command it was given. You want the controller to always be sending something that's an active command. And so this is typically called in control engineering a deadman switch, a dead person switch. It probably should have been called all this time. And so as we think about that, you have to send a command all the time that says, I'm alive, I'm alive, I'm alive. And if you ever don't get that I'm alive command, then the system shuts down. So that's exactly what we have set up for the vehicle. So if I, move on ahead to the next slide here, what we're sending to the vehicle is this breaks down into the two kinds of commands that you can send. You can send your desired velocity, and we're using meters per second in our velocity. You can also send the desired steering angle, and those are in radians. So These are kind of like the two commandments of vehicle control. So there's all the other stuff that's around, everything that you can see. You can turn your blinkers on, the door can be opened or closed. There's all kinds of actuation that's like the creature comforts of driving a car. But really it boils down to moving forward and how fast, and turning my tires and how fast. That's really where it all boils down to. And even if you restrict it to just those two things, there can still be challenges. So to address those challenges and other things with safety, almost everything that gets done requires you to do some analysis first to make sure that it's going to be safe. This is more just for information later. If anybody is going to be interested in developing their own kinds of controllers, they can refer back to this slide, which talks about the V architecture that we use in order to first prototype things on paper, then put them into a simulator. If it works in the simulator, port it and run it with software in the loop. If it works with software in the loop, we're going to inject data that have come from the real car. And if data work after you've injected from the real car, then we're ready to go out and talk about actually running it on the real vehicle. So even though there are 7 steps to this, we've had plenty of examples where we've developed a model and run it on the car at high speed in less than, say, 2 hours. So you're talking about being able to take advantage of model-based design in such a way that you can really rapidly turn the crank in terms of being able to make changes to a system and affect those changes. So that was kind of a large overview of what some of the challenges can be and what some of the inputs might be. I want to next cover some of the basics of those 2 pieces of control, which boils down to sending the steering commands and then sending the velocity commands. Even though I did say that there are lots of different flavors of what you might expect for any vehicle, these are the kinds of inputs that you may expect to be on a car that you might have access to if you want to send control commands to that car. You might send information about the angle of the accelerator that you'd like to see. Those accelerator angles are typically given in something like a percentage, so that you can say, I want the accelerator to be 50% depressed instead of an actual angle of 0.2 radians, because you don't know what the max and min of any particular accelerator might be. You might also want to change the accelerator angle to just be 80% of what it is right now, or reduced by 0.2 of what it is right now. The angle of the brake and the brake change in angle very similar to the accelerator, that you may want to set a specific value, or you may want to just increase it by 10%. You can also, again, set a desired velocity and a desired acceleration. So these 2 kinds of controllers are supervisory controllers that are setting the brake angle and accelerator angle on your behalf in order to achieve the desired velocity according to someone else's cost function. And so you can see that sending the accelerator angle and brake angle, those are like the lowest level kinds of control. In robotics, they're often called like the wrench command. So you're actually maybe setting a specific voltage or setting a torque on something in order to make that happen. Whereas with desired velocity and desired acceleration, that requires some state feedback in order to know how fast am I going right now, so that I can decide how much to turn up the accelerator or turn down the brake, so that I can achieve the velocity that I want. And if you've ever driven in a car with anyone else, you may notice that that own person, the driver of the car, has their own desired velocity controller, and they're manipulating the accelerator and brake to do that. And every person has a different idea of the best way to get to the velocity that they'd like to get to. So as soon as you get to that higher layer, you're already talking about dynamics that either someone else has designed or that you're subject to that you don't know about when it comes to achieving those. And nowhere is that more evident than just having something like cruise control, where cruise control gets you to a desired velocity and then you stay there as best as you can. If you're using adaptive cruise control, it might be taking even more events from outside the car to tell that you're coming up behind another vehicle and you'd like to match that vehicle's speed, for example. And those kinds of control are ones that I'm not really going to delve into too much in this talk, except to say that they exist. The steering control is much easier in that you're typically only talking about setting the angle of the steering wheel or setting the rate of change of the steering wheel in order to follow something. So these are the lowest level inputs to the vehicle, but it's not the kind of control that you may always want to be thinking about doing because, as I've said, we may have layers of control. So here's an example control layer that's based on some papers that came out of the DARPA Urban Challenge about 12, 13 years ago. Where almost all the vehicles that were implemented there had something that looked like this. On the leftmost side, you had something that was calculating the trajectory that you'd like to follow. In order to follow that trajectory, clearly you had to know something about the localization of your vehicle and where it is, where it needs to go. It comes from the trajectory planner, as well as the state estimation that comes to be approximating what's my current velocity, where am I within the locale that I think I'm in, what are the relative velocities of other vehicles around me, for example. And in between the trajectory planner and localization, you have the steering controller that's deciding that you'd like to turn your steering wheel left or right. But in this case, the trajectory planner is determining your goal velocity or relative change of velocity and providing that to some vehicle interface. So right away, we've gone from, we don't just have high-level commands and low-level implementation. We've got high-level commands which have intermediate components, and those intermediate components feed into the lowest level control. This is an architecture that we'll see over and over for control mechanisms because it allows you to put something in between two other things and intercept messages that are coming from one and pass along your own version of that message in order to affect the control that you'd like to have. This is very common for other kinds of robotics applications and really derives from component-based design from simulation, where you might see discrete event simulation, DEVs as it's called, where you can simulate things at faster than real time by determining who should receive a message at what time and what that message value will be. And you can kind of sleep until you get a new message. So this is based on some longer term architectures from back in the 80s and 90s as well. So in terms of steering angle and steering rates, I'm going to go back and see whether my computer ever came to life here in Ubuntu. I don't think it did, but if it did, I would be able to show you what another example of these limitations are. Because if you want to set the steering angle of a particular vehicle, you have to understand that there's dynamics that belong to that. Okay, so we did finally get something that came up here. I'm going to scoot over just a little bit. And I'm going to zoom in here so that we can see kind of what's going on.
Jonathan, we do have a question from Lawrence. I'm going to unmute him.
Please do, yeah.
I was still looking at the previous slide. I was wondering if you could say a little bit more about the delta variable or I guess.
Yeah, I'm naming that delta variable as the tire angle.
Okay.
And so I have actually some kinematic and dynamical equations a little bit later that make that a little more clear. I totally glossed over that.
Okay.
But that's the output of the steering control. So in this case, the steering controller isn't changing your velocity. It's just setting the tire angle that you should follow. It's depending on the trajectory planner to set a valid velocity.
All right. Thank you.
It's a great question. So I hope everybody can see it, but I'm going to zoom in maybe even more until the front tire is totally in the frame here. And I'm going to next pop over to pull up an example of what we were doing before. So in this case, we were looking at the command velocity from the turtle. I'm going to use the same commands that we were using for teleoperating the turtle. So ROS run, turtle, sim, turtle. Did I misspell turtle sim again? No, turtle, teleop key. But in this case, instead of saying turtle one command cell, I want that to be mapped to cat vehicle command bell. And so now if I press the left button, we should see the tires move. In this case, though, they are not moving, which is fantastic. Let me see if I press forward if the car actually starts to move forward too. It could just be that my computer is totally overwhelmed with what's going on. In theory, we're able now to actually send these commands to the car and make the car move around. Although in this case, the car is just clearly not obeying. And so that's part of the benefit of doing a live demo of something, is that you can expect it to fail. But if I go back now to, I'm just going to close some of these things in case we later try to do something with it, and I want to try to resume this either in the office hours or elsewhere. So if you're able to use one of these systems like ROS, you can remap the inputs and outputs of a system in order to be able to use something intended for one system on another system. And as I go back now to my slides, you can see here that I've got a steering angle that's set over to the left. Because I don't have a video of this, I can't show it very well, but if you actually go into the Turtle and you press left, the tire just automatically goes all the way over to the left. Like, it's not a great systematic approximation of how tire angle changes. The tire angle just instantaneously moves as fast as it can. And that's really a danger because the simulation environments are very tricky to match to what's really happening. So you can expect, for example, and this is some system identification we did on the CAT vehicle about 7 years ago, if you wanted to set a 40% angle of the tires, so if you want to move the tires to 40% of their maximum value to the left, it takes about, to get to steady state, a little bit more than 1 second to get that all the way to that 40% angle. And so you can see that there's a little bit of overshoot that belongs to this. There's some settling time involved in this. It's kind of a classical controller that they're using with PID probably in order to get and obtain this outcome. But it's something you have to consider as you're doing your controller. You have to understand that if I'm setting a steering angle, it actually takes a little time to get there. And that's something that's often neglected in simulation, especially vehicle simulation. Another thing that's often neglected with vehicles that are dynamically interesting is that you also have to consider the vagaries of the overall topology through something called the Acqu model. And in the Acqu model, this is something that almost nobody really needs to know about. I'll be honest with you, right? To drive a car, you don't need to know the Acqu model. But if you want to simulate a car, you kind of do. And we're going to try one more time to see whether I can make something interesting work here. And then this may be the last time I try to do something fancy. So the Acqu model is one where it actually was developed, I think, and the basics of it were developed as rack and pinion back in the 1790s or 1820s or something like that. It's actually kind of an old system for why it works. But I'm going to walk you through, and I hope everybody can see this now, kind of some drawings of how this works. It's animated a little bit to show you what some of the challenges are. So if you begin with your vehicle and what your vehicle is doing. Oh, I see we have another question here.
Jonathan, we got another question, yeah.
Short question. Since your sensor is on a different computer and you use ROS to send the commands to the car, it's quite a latency between what you observe and when you execute it already, before even the wheel starts turning. Doesn't it introduce instability in your control if you really want to do obstacle avoidance or something like this with your car? Mm-hmm. I kind of understand that you can do top-level path planning, but if you really want to use it to avoid something, I guess your infrastructure may be a little bit slow to respond to things.
Yeah, that's a great point. And it's one that I have some data a little bit later to show how bad that is. And so if we can defer that until maybe I get to the part where we're trying to do velocity control, then you'll start to see where some of those challenges really pop up. But the short answer is that typically the latency in sending the command is on the order of a couple of milliseconds, 1 to 2 milliseconds, depending on how fast you want your controller to run. And that's about the same order that you have on the CAN bus when sending most of the messages that are sent on a CAN bus for a car for steering or for velocity control are between 20 to 50 hertz. And so that kind of delay is mostly acceptable as long as your system is operating fast enough. So I think I got to this point where I had this really uninteresting car. I always tend to drive, if I'm going to move a car in this direction, I have this sort of unintuitive arrow that indicates that it's kind of pointing there. But that represents the maximum and minimum steering angles that you might expect with a vehicle. So I kind of indicate it in that way. And so we're going to put some tires on this bad boy, 20 R45, 72s, or some other number that I don't understand about tires. And I want to show that each of those tires has its own dynamics and its own path. So I have a tread width for my vehicle, and I also have something that's going to be called the wheelbase. So the wheelbase of the vehicle, the L, really controls how far those tires are apart. And so there's like the longitudinal distance L as well as the lateral distance T that is going to govern what some of the equations of motion are for our car. So if our car looks something like this, and we want to follow a path, following that path is not as easy as just moving left and right because the car has its own dynamics. And we are typically going to measure that the path is following over its center of motion, which is the center of the rear axle. Unless you're doing some high-speed driving on top gear, the path of your car is always going to be right over that rear center axle. So we're going to pretend like we have this imaginary middle tire that's governing what the vehicle is doing, and this is what's called the bicycle model of control. So if you want to use the bicycle model, you assume that you're just setting an idealized tire angle, and you're depending on the dynamics of the car and its physical properties to come up with the rack and pinion to set the individual tire angles so that you don't end up tearing up your car. And so as we're going to follow this path, if we want to use this model, it's pretty straightforward when we're going straight that all of these lines are going to match up for every one of the tires. But as soon as we start to turn, it fails really badly. So if I were to take each one of these angles here and draw the circle of the path that I'm trying to follow, first we see that the tire that I'm following here, if it was to just be tangent to that curve all the time, this is where it would go. But if we do that for the inner tire and the outer tire, and then we compare the path, at some point over here on the left, if I can just annotate this over here, you see that the tires actually cross over, and they cross over again over here. So if you wanted to build a simulator, which is something that many folks have tried to do in the past, to simulate what my vehicle is doing, and you forget to take into account some of these kinds of things, your simulator will actually throw your car into 1,000 pieces as long as you have little bits that are holding the tires together or pieces that are holding your chassis on. We did some preliminary tests with the CAT vehicle when we were just using an existing controller that was on a unicycle robot. We just gave it a wheelbase and we told it to take off, and then one of the tires flew off. And I was like, that was weird. Let's try that again. Maybe I just didn't make the stiffness hard enough. But no, it just really doesn't work. You have to choose this ideal tire angle based on the wheelbase and the tread width that you have so that you can change, and this is what Ackerman's model does. So you have this line that goes through your rear tires, and you have a line that goes through your idealized front tire. And with this, you can come up with an idealized path that your car will follow, which is not exactly the front tire's angle. The front tire will actually follow this path. It's just outside the lead path. And likewise, the inner tire and the outer tire will follow their own paths as well. And so once you come up with the ability to use Ackerman's model, it allows all the tires to move on their own and prevents this unnecessary tread wear. What was happening in the olden days when somebody came up with the rack and pinion was that the wooden spokes on their buggies were just exploding and the tires were breaking all the time because every time they turned, it was producing this unnecessary shear on the inner and outer tires whenever they were turning, that they were being pushed normal to where they were trying to go. And so kind of to summarize, what do you see and how do you control with these tire angles? You have a bunch of different equations that can help you get the idealized turning path that you'd like to get. And so whenever you want to set a desired path, you're setting your turning angle based on trying to follow that path, based on essentially what's the radius of your path. So you set an idealized tire angle based on the radius of the path that you want to follow. And from that idealized tire angle, you can approximate what the tire angles of the other tires would be based just on trigonometry. And so you have an inner radius and an outer radius that you can ascribe to this. You need those inner and outer radii in order to make sure that you can avoid an obstacle that's on your inner path and that you can avoid an obstacle that's on your outer path. So even though this seems maybe just like a simulation detail or a construction detail, unless you're considering some of these things in your validation criteria, it's really tricky to do. But again, once you've got a radius of curvature, little r, from that radius of curvature, you can come up with, based on your wheelbase, the idealized tire angle by just taking the inverse tangent of L over R. And that's going to give you the tire angle that you should set based on the radius that you'd like to achieve. And if you're interested in seeing more about that later, I think this should be going away now, and I'm not sure why it's not. There we go. If you want to find out more about that, it turns out that actually the most popular YouTube video that I have ever done is explaining the trajectory following with the Ackerman model. So I'm closing in on like 100,000 views of that video, which is kind of unreal.
Question that also came up there, how do you decide the origin?
How do you decide the origin? The origin comes from the radius of curvature that you're expecting. So if you see that you have an instantaneous curvature that you'd like to meet, from that instantaneous curvature, you decide the origin of the circle. And if the circle is too small, you're going to get an inverse failure with the inverse tangent. It's not going to make any sense. You're going to set a tire angle, and it's going to be for a tangent value that you can't achieve. And so this was my backup in case that didn't work. We're just going to skip all of this now. So here's a great example of how to come up with what you want that steering angle to be for something that you want to do based on the instantaneous path data. So in this case, I'm not actually determining that I want to follow a particular curvature as much as that I'm saying for my car, I'm not on the path right now. So I can estimate my error to the path, E here. And with my error to the path, I can also approximate the error to my, I can get an instantaneous value of my angle. So my angle of T is with respect to where the path is normal. And so my C here is, or I guess psi. Psi is telling me the angle that I have to the instantaneous curvature of the path here. So based on my error and based on the instantaneous path error that I have here and my current velocity, I'm going to use this equation in order to determine what I'd like for my tire angle to be. And maybe there was another question. I thought I saw the chat light up a second there.
There is. The question is about, in a modern car, whether the individual tire angles are controllable or is it mechanically enforced to be correct relative to each other?
For some vehicles, it can be mechanically controllable for each individual tire, especially if you've got a four-wheel drive car or a hypercar. Those are ones where the individual wheel, in fact, the individual wheel speeds can be controlled, and the individual wheel speeds are often used in order to make sure that it reduces tire wear when you want to reduce tire wear. But largely what happens is that somewhere there's an onboard component that's converting and doing some lookup table analysis to say, at this speed, with this tire angle, this is how I need to move all the other individual tires. And so there's an onboard computer that's doing that, and they kind of don't trust us to do that. We would probably need to hook in and connect voltages to each of the individual tires in order to make that happen. Okay, so this example trajectory following controller is based on something developed by Gabe Hoffman for the Stanford racing team in the 2006 Stratford Grand Challenge, and I think used by many other folks since then, including us, for being able to follow a reference trajectory. And you can get some really great results with this because you've got the tangent function there. This is basically creating a controller that avoids chattering when you're following along a saddle point, and so you don't end up with going unstable based on your frame rate or based on some noise error there. And so it has some really great properties. But the pesky element here is this V velocity of T here. So I'm depending on somebody to give me a reference velocity that's valid for a specific curvature, which is not something that's always useful. And with, I hope, a little bit of forgiveness from anybody who may have been a part of this team who's on here, there's some previous examples of what can happen if you give a turning angle and you don't think much about what the reference velocity should be. You might end up saying, is my camera upside down or is the car upside down? So you have to be really careful when just sending these commands to a vehicle to make sure that it behaves like we think it should. And so in order to accommodate this, one thing that you may consider doing is coming up with some controllers that will fix the velocity. If you provide an input velocity that's either flat out wrong or just too aggressive, we'll fit that to a particular driving profile. So I'm treading now a little bit close to the data side that we're going to talk more about on Monday. But if you had information from a driver that said, this is how the driver typically drives, and you just record the steering angle percentage compared to the velocity that they're driving at, there's actually a pretty well-defined curve that falls off pretty hard here as you get to higher speeds. And it turns out we almost never have high steering angle at high velocity. And so we can develop some controllers, and this is not something that's, maybe that interesting for you to understand exactly what are all the vagaries and the mathematics behind it, as much as to say you can just create this controller and put it in the car, and it will handle setting the velocity for you if you provide the wrong velocity. It will regulate your velocity based on the steering angle it can achieve right now, based on your definition for what safe means. So going back to the comments on what does it mean that we can control individual wheel angles, there are lots of controllers that are kind of like this, that are translating instantaneous velocity and desired steering angle into desired or into actual steering angle and velocity for individual wheels. So you can do some fairly straightforward control here in order to determine for this velocity controller how to achieve the actual velocity that we can get now if we start outside the safe space and we want to get back into the inside state space as quickly as we can. That this kind of implementation allows us to make that happen. So we can even define a couple of different driving profiles depending on what we want to follow. So here's a normal comfort line. Here's one that's really comfortable. And then this dotted line here is me driving in a parking lot. Or if you may want to consider it maybe as my grandmother driving around. Like every person has kind of their own individual curve that they follow. So why did I go through that example there? You'll remember that in the beginning we talked about having the steering controller that's kind of in between your trajectory planner and the vehicle interface. This is adding another layer there, which we call the comfort controller or safety controller, however you want to think of it, right? So that safety controller is allowing you to command exact values still for rate of change of steering, but it's regulating your velocity. So it's preventing you from sending a velocity that's too high because that would result in catastrophic failure or unsafe behavior. And so this is indicative of the kinds of control architectures that you see and why we depend so much on things like the robot operating system to do this, because we can hook the boxes up in a certain order and then have the individual components be tested themselves on input and output data streams so that we can validate that they seem to be working. And this is essentially the state of the art for what you see in producing low-level behaviors on existing vehicles today, that individual components are spec'd, their input-output definitions are given, and then once they pass validation testing and requirements testing from whoever's purchased that, if it's Toyota, they might purchase it from Denso. If it's Dodge, they may purchase it from Mopar or another supplier who's developing those low-level controllers. Once it passes that, then they feel comfortable plugging it into their car and making it work. So I want to spend a few minutes talking about some of the actual limitations that we have in vehicle control. And these are largely based on physics, but it also gets into some of the challenges that one of the questions, I think it was Darius mentioned about the delay that you might see just from being hooked up in a network. So our vehicle that we bought came with sort of a stock cruise controller that was a predictive receding horizon controller that would try to match input velocities as they would come in. So you could provide a series of velocities that you'd like to follow over the next, say, 10 seconds. And it provided an optimal controller that would try to match those velocities as best as it could. So if you know your velocity for the next 10 seconds, it's a great controller. And for a cruise control example here, you can see that we start at time 0. At around time 6, we provide a reference velocity that goes up, and then we stay at that velocity of about 8 meters per second. And so as we start to drive here, you see that we track that velocity, and at around 12, 13, 16 seconds, we get to steady state. So 16 seconds to get to 8 meters per second is not particularly aggressive. You would probably be asking why we were going so slow, or if we were still in the drive-through if somebody was driving that slowly. But let's just say, for example, that's kind of what we've got right now. That's our cruise controller input. So you provide a reference velocity, and the vehicle provides accelerator angles and brake angles in order to make that happen. Now, if you want to zoom in on this a little bit, again, you can see here that actually, I guess the steady state value that I found here was at around 20 seconds. So I only thought it was in steady state at 16 seconds. We actually dipped down below there. But then once you get into steady state, it maintains your steady state pretty well. But if you provide any input to this instead of just a reference input that's a constant, you can end up with behavior that's not actually as good as you thought it might be. So in this case, we're trying to track a reference velocity that's a sinusoidal input between 4.5 and 3.5 seconds. And it's not doing so well. We're out of phase almost with the velocity that we're trying to follow. And so if you're trying to use a vehicle to do something other than get you from point A to point B, if you actually want to track a reference input that is not predictable in some way, then you may end up with challenges with the current state of the art for what's there. And so in this case, again, we're about 3 seconds late when we hit our trough here, which is not great. And so if we try to provide another kinds of reference velocity, in this case, I had an existing drive that I did, and I thought maybe the vehicle would just be able to follow my drive. And the answer was not great. So we're trying to follow a reference. If you can follow my mouse here, we're trying to follow a track of reference velocity here. It hits the trough at about 47 seconds and then goes back up. And while it's going back up, our vehicle actually comes to a stop. So the ability to track a time varying function with a cruise controller is just not good enough. You know, if you do this and you want to do something like hypothetically control traffic flow, if you wanted to do something interesting like that with your car and you were to use this, you're trying to dampen traffic flow and you're coming to a stop in the middle of the lane. So it's really kind of unacceptable. And if you don't listen carefully to the instruction manual of the vehicle, you may find that you would actually hit some problems with PID windup. So those of you familiar with control know that if you start a PID controller and you have error in that PID controller that's being integrated, then if you just sit there and don't provide any inputs, the integration portion of your PID controller continues to go up. And so it takes a long time to overcome that. So in this case, we actually just waited, I think, for 7 seconds and then started the car with a reference velocity of 4 meters per second, and we ended up at 14 meters per second before we ended up stopping. So this was not a great outcome, right? We needed to correct this.
Jonathan,
so this gets back now.
We have another question.
Pardon me? Oh yeah, go ahead.
Ronan, you're unmuted.
So in the previous example where you're saying the car wasn't able to follow the prescribed time series, so why exactly is that? Is it just like the accelerations or the jerks are too sort of harsh for the car controller, or like what is the problem there?
Yeah, it could be that the controller is just not expecting that. And we should never fault the controller for failing to behave on an input that it wasn't designed for. You know, if our system is stable for step input, but not for ramp input, we should not complain when it would provide a ramp input, you know. And in this case, most controllers that exist for cars right now are meant to track an existing velocity or track the velocity of a vehicle in front of you within reason. And so it's really rare that we want to do something more interesting than that, which is why we kind of had to do some, research work to figure out what can we do in order to make this happen so that we can actually do something more interesting.
Okay, I see.
But it's not that the reference trajectory was too aggressive for any car to follow, right? It was that this reference trajectory is one that the supervisory controller that translates an input velocity into brake and accelerator commands, that kind of controller was not anticipating needing to do this.
So what exactly do you mean by like anticipating it needing to do that? Like,
like the person who designed that said, this is great. Every input that we're going to get is going to know for the foreseeable future how fast it needs to go. So if you're designing a fully autonomous car, and that autonomous car is just meant to get you from point A to point B, and you're on a DARPA racing track, right? Then you've got a receding horizon controller that assumes that I'm in control of what I want to do for, say, the next 10 seconds. So if I were to provide 10 seconds in advance of what I want this controller to do, the controller will do much better. But if I'm changing my input from second to second and I have no horizon in the future to know that I need to react to something, then it's going to behave really badly. And many of the more interesting controllers are ones where we're reacting to the vehicle ahead of us, and the vehicle dynamics ahead of us are going to dictate how we need to react.
Okay, I see. Thank you.
But it took us a long time to figure this out too, because we're like, it's a predictive controller. How bad can a predictive controller be? Well, it turns out if you change your input a lot, predictive controllers are pretty terrible. And again, it's not that they're bad. They're not designed to do that, and so we shouldn't fault them for that. And so going back again to the software interface layers that we had talked about earlier, because we're using lots of different layers to make this happen, we can inject new kinds of control at different places so that we can take advantage of, developing a little bit of new technology in order to make this happen and just putting it in at the right place. And so with apologies, again, to those of you who have Clippy and Clippy is your favorite, that's what we're trying to do. We're trying to build a model and analyze that model. Once we're happy with the analysis, we want to generate the code and then have it work. And so with, I may be able to talk a little bit more with this on the data access side. We're treading into data territory again. But this is an example of where if you take a system and do a little bit of system ID, then you can build a model with that system ID within a tool suite. Once you're happy with how your system behaves there, then you can take the inputs that you got from the real system, see how it tracks. And so now we can actually simulate that using our Gazebo simulation to make sure that we're not going to send some commands that are weird. And so in this case, we actually track pretty well with what we're expecting. And then we go out and track it with just a cruise controller. We see that it's behaving pretty well with the cruise pole at 3 meters a second. And now when we try to follow this representative curve, you can see that we're actually tracking it much better. So we're still overshooting a little bit, undershooting, you might think here when braking. That's a safety design decision. We're braking a little more than we thought we needed to because we're better off braking a little more than accelerating a little more. But we're no longer coming to a stop when we get to this curve. We're dropping down to, say, 1.5 meters per second. And this is a zoom up of that. We're dropping down to, say, a little bit lower than we want, but we're not actually resulting in coming to a stop. So these kinds of low-speed tests, this works really well because we did a lot of linearization to make that happen. At high speed, the models that we need to do and need to work with are much higher risk, and so we have to be a little bit better with thinking about this. So we're a little short on time, so I'll skip kind of the Socratic method here. But if we want to update a velocity in a lead vehicle, that we're going to be doing up to, say, 22, 23 meters per second, which is about 50 miles per hour. One thing I do not want you to ever consider doing is that you would have somebody sitting there with a terminal and typing 22.2 and pressing enter. Because if they accidentally press 2.2, your vehicle will follow 2.2 exactly because you gave it that command. And any vehicles that are following you will pretty soon be in your backseat. So in order to be able to do, again, for safety reasons, things like this, we typically depend upon reactive dynamics or synchronous reactive systems, such as state models, that allows us to develop a system that we will move through. And I've got a zoomed in model here. So in this case, we begin by going 0 meters per second. And then while we're in this state, we increase our output velocity. And once our output velocity exceeds a certain amount, we transition to a mode where we're stopping. So this particular state model is going to speed us up and slow us down, speed us up and slow us down, speed us up and slow us down. And we have a different version of that here, which we tested with hardware in the loop at high speed, where we got to a reference velocity, increased our velocity, decreased our velocity, increased our velocity, decreased our velocity, so that we could validate that the system seemed to be behaving well. In this case, again, with the configuration management that you have, we're actually using here the existing cruise controller that we had because it's designed to hold a specific velocity. So you can choose at any given time, do I need to be able to track a predictable velocity or do I need to be able to track an unpredictable velocity? So those two, you're kind of switching back and forth between which of those controllers you'd like to use. And that's a useful thing to think about as you're doing this kind of work. I think the last thing, and this is what had prompted the question before from Darius, if you're moving along while you're computing a control decision, and this is true even for systems that are not in ROS, you might get a state update and you don't finish your control calculations before you get to the next state update, which results in you missing that deadline. And so in this particular case, the control calculation misses the deadline by some way. And this is really common to happen in optimization-based controllers. So especially if the obstacle is moving and we miss our state update, I think this is exactly what Darius was saying. Here, this is epic disaster. I was trying to move. I saw the obstacle moving. I was trying to move, but I couldn't finish my control commands fast enough, or there was latency in the network that made that happen. So again, predictive control is one way that people have tried to account for this, that if you can have a fast loop and you can predict what your obstacle is doing, then you can provide reference inputs that allow you to also predict that obstacle's motion and move around it. But there are some...
May have had a follow-up question for you.
Oh, yeah. Go ahead.
Yes. One question. From your architecture, I understand that the sensors are connected to your computer and you allow others to connect on a different machine. The problem is, of course, if you try to move the sensor data over some slow network, you increase actually the to be evaluated. So you have to move the data between the computer you acquired it from and the computer which is analyzing. And this is additional delay you introduce to the system.
Yeah, it's very true. The way we've typically done it is that we've had, if something needs access to a tremendous amount of data that's being acquired right then, you can actually place that component on the computer that's acquiring those data. And then you don't have to ship it to more than one computer on the network. And so that's one way to mitigate that, is that the controller may run on your machine and the inputs that you're getting is a filtered version of what came from the real data.
Yeah, okay.
And because you can deploy which thing should go on which machine, that's what makes that possible.
Mm-hmm. Okay, thank you.
Yeah. So again here, if we're trying to avoid an obstacle and we have a really narrow or small margin for error, you may think that if I need to account for a small margin of error and if I want to be able to be really close to those obstacles, by cracky, I need a really accurate model. But the problem with a really accurate model is that's going to reduce your feedback time. It's going to reduce the amount, it's going to increase the amount of time that it takes for your optimizer to finish, which is going to reduce the frequency of your controller. And so this is something, there's some active research in order to overcome this by lots of different folks called computationally aware control, where you're switching back and forth between your predictive model based on what your expected margin of error is. That allows you to do that. And so essentially these competing constraints are something that you should be concerned about as you're developing a controller. And I had promised earlier that I would eventually have some kinematic and dynamic models of vehicles that might be used. The top one is much more of an Eulerian dynamics that does include the wheelbase and the tangent of the tire angle. And so that's an accurate representation of what you get for a vehicle that's in motion that has a wheelbase that does need to follow a particular trajectory in order to move. So this is the rate of change of angle, again, is dependent on your velocity. If you're moving faster, your rate of change of angle will be different. The bottom example takes into account the tire stiffness. It takes into account some moments of inertia. It takes into account all kinds of other things. And it's much more accurate, but it's also much more prone to modeling error and results in many different things that might be happening. So for the sake of, again, further discussion, or if people have questions in office hours, we can talk more about what some of those dynamics are. I want to wrap up in just a couple of minutes, but I thought I would also include, for sake of completeness, that everything that model predictive control might do is based on producing a sequence of control inputs based on a sequence of expected state outputs. So you do have some typical receding horizon. And you're supposed to be providing the input sequence at your expected rate based on optimization of some cost function. So I've not included much detail about the cost function here, except that I do have some state constraints that I want to make sure that I avoid that are maybe obeying the speed limit. It might be avoiding an obstacle. It could be trying to reduce the frequency at which I turn my steering wheel so that if I integrate the steering wheel change over time, that it's the slowest amount possible. Or it might be also that I'm including information about my final destination and where I want to go. So not only do I want to move smoothly and avoid obstacles, but I eventually want to get to the place where I'm trying to get to. And so considering this cost function and taking the arguments, taking the minimum across this based on the only thing you can change, which is your control input, and keeping in mind that your control input is a product of the state equation that we see up above. This is what makes receding horizon control and MPC so complicated, because you've got a lot of computation going on and you still need to send control inputs at any time. So it can still be really useful when looking for these optimal conditions or optimal-ish good enough conditions. But if you're optimization is non-convex, or if you have competing constraints, you could end up avoiding one obstacle but hitting another one. So that's not good either. So coming up Monday, we talked a lot about the control side today. On Monday, we're really going to lead into more aspects of how do we extract data from a vehicle? What do we do with those data? How do we interpret the data? And how might we consider using it in learning or in validation? We're going to look a little bit more at some of those interface layers at architectures for where you can insert your controller. And we're going to also explore more about how do we extract models that we might be using to build new kinds of abstractions that would lead to new kinds of properties. With that, I think I always have to remember to thank all the sponsors that I've had that have produced a lot of the data from before. And maybe at this point, we can open it for Q&A.